All right, looking at quiz number 1 from this year, 2015. If we're going to look at number 2, kind of this whole problem, 2, 3, and 4, I guess. So what we have here is a Friedel-Crafts acylation. The key to remembering this is we're adding an acyl group, right? That's the carbonyl. The other big key for the Friedel-Crafts acylation is no rearrangements. We're not going to make a carbocation. No carbocations, no rearrangements. That's the key. All right? No rearrangements. And remember, we use this as a way to access, right? If we wanted to put a single carbon chain, a straight chain, right? Because in alkylations, like we did in lab this week, or any alkylations, you form a carbocation as your super electrophile. And what happens if you form a what can happen? If you form a carbocation, what can happen?
If there's a more stable,
if there's a more stable product, it will rearrange. Acylations, no carbocations, no rearrangements. So don't do it. All right, don't do it. So the actual product here, you should be able to, right, at some point for most of these, you should be able to look at these and just give me the product, right? I expect you to know the mechanism, but you also should just look at it and say, oh, product. What's the product going to be in this case? It's an acylation, so we're adding the carbonyl group to the benzene ring. Right? So you should be able to look at this and just know that. So that was 2. For number 3, it asks for the actual activation of the super electrophile. Okay. So here I saw a couple different things. There's a couple different ways. I mean, really, at the end of the day, you could do this a couple different ways. I'm going to show you the way I showed you in class. All right. So what you need to do is you have your electron lone pairs on your chlorine. Right. Every reaction, somebody's an electrophile, somebody's a nucleophile. Aluminum's a metal. Right. If you see metals are always going to be delta plus. They're going to be good electrophiles. So that means the other thing has to be the nucleophile. And so in this case, the chlorine lone pair is going to attack the lone pair. And that's going to kick out another chlorine. Now we need to remember to, of course, balance our charges. So who got electrons? Who has a negative charge now? Who got electrons? One of the chlorines did. Good. Now who lost electrons? The chlorine attached to aluminum and the carbon, right? Notice, right? This chlorine's giving up electrons. This chlorine's getting electrons. If you give up electrons, you're going to have a plus charge, right? You just lost electrons. So the plus charge is here. All right? Good. Now this mechanism is a little different because there's lone pairs on the oxygen. What we can do is these lone pairs can come down, right? Because is the chlorine happy with a plus charge? No. Lone pairs can come down, and that will kick out the chlorine. Right? So now who lost electrons? So now if we go to the other side, the oxygen lost electrons, right? So now there's a triple bond there, and the plus charge should be on the oxygen. You've regenerated your catalyst, and Cl minus is still floating around, right? This is the way I like to do it because in this way, right, some different ways you could draw a resonance form where electrons could come up here and you have a plus charge on this carbon, but that makes people think there's a carbocation. There are no carbocations in acylations. There's no carbocations because there's no rearrangements. So that's what I like doing it this way, so I avoid having a plus charge on that carbon. I disagree with the book. The book does it with the plus charge. I think that's silly. Right? I would do it this way. So what have we done though? At the end of the day, if we knew that this was the product, we need to make, right, this benzene ring in electrophilic aromatic substitution. Electrophilic aromatic substitutions, what is the benzene ring always? Is it the nucleophile or the electrophile? It's always the nucleophile, right? So what does this have to be? That means this has to be the electrophile. So we need to make that carbon delta plus, right? and what we just did here, right? So don't forget about, if you know this, right, be thinking about where you're going, right? What am I trying to do? I need to make that carbon delta plus. And as it is right now, right, even though the plus charge in the oxygen, a carbon and an oxygen are bonded together. Who has the electrons? Oxygen or carbon? Right. I don't care what the formal charge. I don't care what the formal charge says. This carbon's what's delta plus. Yes? All right. So let's keep going. So number 4 says then, draw the mechanism with arrows showing the formation of the product including sigma complexes for the reaction above. So we've made our super electrophile. Now it's asking us to go ahead and show the mechanism for the formation of the electrophilic aromatic substitution. Now I'm going to go ahead and jump ahead and number some carbons. I should have been doing it all along, but this isn't my first rodeo. 7, 8, let's say. 9, 10, 11. So it doesn't matter which carbon I pick in the benzene ring. Why not? Because they're all the same. So we attack carbon 7. Carbon 7 has 4 bonds right now, right? If I make a new bond, do I need to break a bond? You better. Who has the plus charge now? To balance, right? Balance my charge. Who should have the plus charge? Carbon 2. Which carbons got bonded together? 1 and 7. Yep, 1 and 7. Plus charge here. Right? So now this is the first sigma complex. And you always have how many sigma complexes at least? Always at least 3, and if you're lucky, 4. Right?
Have you ever done an example before?
Yep. Yep. So like So if you have an electron donating group already on the ring, it directs ortho and para. Right? So you can do resonance structures of the starting material to realize that. And you can also do sigma complexes, and with the electron donating group with lone pairs, you will get a 4 sigma complex. Yep. And that's really good because that one has a full octet. So if we want to draw some sigma complexes, let's keep going. Let me go down here. All right, there's one. You can draw another one. It looks like there are now 3 sigma complexes. 3 you asked for. Okay? So that gets us the sigma complexes. But then we also need the final product, right? So I'm just going to redraw one of the sigma complexes. I'll redraw the first one. All right? And at the end of the day, it's a substitution. We're substituting what? We're substituting off an H of the carbon that the new group is added to, right? Not the carbon that has the plus charge. All right. So the H probably going to be a Cl minus from before. Take CH. What kind of reaction is this? That one I just drew? It's an elimination, right? We form a pi bond, right? Overall, the reaction is a substitution, but this particular step is an elimination. And it's fast, right? Why is it fast? Why would it be fast? What did I reform? I reformed the aromatic system, so that's going to be a fast step, right? And then we also have the AlCl3 has been regenerated because it's a catalyst. So let's look at 6. So the tricks I tried to pull on you guys. the tricks I accomplished, so tricky. So KMNO4 is an oxidant specifically towards benzylic CHs, right? So if it has benzylic CHs, whatever was there is going to become just a carboxylic acid. Everything else gets chopped off. So essentially, we chop off that, and this becomes a carboxylic acid right here, and this becomes a carboxylic acid.
So because of those three hydrogens on that methyl?
Yep, any benzylic H, any benzylic CH. If there's one benzylic CH, everything gets chopped off and it becomes carboxylic acid. This takes one. OH, OH. And if this is carbon 1, this is carbon 1. This is carbon 2, that's carbon 2. Everything else is just gone. Everything else, so it becomes a dicarboxylic acid in this case. If there's benzylic CHs, chop everything off, turn it into carboxylic acid. The benzylic oxidation. Okay? So I was trying to make it tricky because I want to see do people know the benzylic position is. Right? Off here, people thought this was the benzylic position. Right? But benzylic position is what? One right off the ring. Right? That is correct. All right, this one has an alkyne hanging out and a benzylic ketone. The trick here is,
Everything gets reduced.
right, if you have H2, assume you have an excess of it. It's going to reduce everything. It can. If it's possible, it will reduce it. So what's it going to reduce? Of course, it's going to reduce the benzylic carbonyl,
Everything.
which we learned, but it's also going to reduce the alkyne like we learned before, right, chapter 6. So the product, and this is where I saw a lot of people make mistakes, was they didn't number their carbons. We added carbons, we lost carbons. 2, 3, 4, 5.
Wait, so what was
How many carbon pieces are right here? How many carbons are on this piece?
2?
2, but I saw a lot of people put 3 or 1.
So what was the trick?
The trick is, not trick, but H2, right, not only reacts with benzylic ketones like we learned right in this unit, but we also learned, right, don't forget, they still react with alkynes, just like always, right, all the way. They reduce them all the way to the alkanes, right, just like they react with alkenes, they turn them into alkanes.
Why would you drop the oxygen?
Right, because it's a benzylic carbonyl. Remember, there's 3 ways to reduce benzylic carbonyls. H2, platinum carbon, zinc, HCl, and H2, and then H2, OH minus. Also, those 3 ways to reduce the benzylic carbonyls.
So you just dropped everything besides the carbons,
Yes.
no matter what it is?
As long as it's benzylic. And then this always happens. Right? Aromatic ring stays the same. That doesn't change. That's too stable to react. But I need to draw out 6, 7, 6, 7. Good. And then the other one in 6 I showed you in class today. Right? Just basically needs to be a benzylic. If it's not a benzylic carbonyl, you're not going to reduce it. It has to be benzylic, right next to the ring. So let's take a look at essentially how resonance structures, how we can differentiate between electron donating and electron withdrawing groups, and then some other factors at play. So essentially, electron donating groups fall in one of 2 categories. Either they have lone pairs right next to the ring, or it's some sort of alkyl substituent like toluene, something like that. So toluene is not, it's electron donating, but it's not that electron donating, right? Because it's only donating via hyperconjugation, whereas lone pairs is a better, right, more efficient way to give up electron density. But be careful, right? Are all electron withdrawing groups or electron donating groups created equally? No, right? For instance, the one I have drawn here, what kind of molecule is this? What kind of functional group is this? ester, good. So the deal here is the lone pairs can donate to the ring, right? And we can draw those resonance structures. But could this lone pair also donate back this way?
Yeah.
Yes. So if you were to compare these two electron donating groups, this of course being anisole, right? Which one's a better activator? You would say the ether, this anisole is, because this has resonance structures only going one direction. Whereas this one has resonance structures going towards the ring, but also back the other way. Right? So even though this O and O, this is a better electron donating group. And there's some pretty good sampling questions that ask you about this and go through and say, right, which ones are better activators or deactivators.
Okay,
So make sure you know why though, right? This is because this has an alternative resonance pathway essentially.
so the donating are activator groups?
Donator activators. And usually they have lone pairs, except for alkyl groups. Right? This is a carbon, then it's just hyperconjugation that's stabilizing. So let's rank these three electron donating groups. Which one do you think is the worst, the least electron donating? The toluene actually is, right? Lone pairs are better than, toluene is like it's the slowest of the fast guys. It's the Wenzel molecule. Right? So this is the least activating. All right? Lone pairs are better than always going to be really good. But then between this ester and this ether, this would probably be the most, and then this is in the middle. Nope, wrong way. What am I saying? Lies. The ether is the most because it only has resonance one direction, and then this would be the middle activator because it can go resonance towards the carbonyl as well.
Can we do a withdrawing one?
Sure. So, a withdrawing.
Just take a pick of it anyways.
Let's say aniline was in with the rest of those ones that we were just doing, would that be the best?
Aniline would be the best, right? Because nitrogen is more willing to donate electrons than oxygen. Here we go. So you have three electron withdrawing groups. So these are all deactivators. We have benzonitrile, methyl benzoate, which you guys use actually. This is an ester. And we have benzamide, right? An amide. So we got to decide which of these carbons is most electron withdrawing. I don't know if I know the answer to this now that I've done this. Yeah, I think I can figure it out. I can guess. We'll come to a logical conclusion. I don't know if it's exactly right, but we can get to a logical chemical answer here. How are we going to decide? We need to look at carbon, carbon, and carbon, and decide which carbon is the most delta plus. So how are we going to? What's the analysis we should look at here? Huh?
You look at the atom next to like the electronegativity.
Right. So I think. So yep, we're going to look at the carbon, same carbon, and say what is it bonded to. So I think the top right one is the most deactivating, right? Because this carbon's bonded to an oxygen that has 3 bonds to oxygen.
So it's the most electronegative is which one?
Because it makes this carbon, right? We need to figure out which makes this carbon the most delta plus, right? Because that's what's pulling away electron density. We need to find the carbon that's most electron deficient. And the way to look at it though is say, okay, well, what is this carbon bonded to? This carbon's bonded to a nitrogen 3 times. This one's bonded to a nitrogen once and an oxygen twice, right? A sigma and a pi bond. This one's bonded to an oxygen and a oxygen as well 3 times. So, what's the worst case scenario? What's the most electron withdrawing? This is probably the most electron withdrawing
So would that make it
group.
the least reactive?
So that'd make it the least reactive, right? It'd be the most deactivated. And then I would say this would be the least, and then obviously the amide would be in the middle. Right, just based on, right, the carbon, how delta plus it is, based on what it's bonded to. So I have a pre-drawn here a benzene going to this di-substituted molecule, the tert-butyl and a SO3H. So let's kind of analyze this. So we know the tert-butyl is a activator, and we also know, so it means it goes ortho-pair, right? All activators are ortho-pair directors. Right, so this is the T-but. We also know it's bulky, right? So hopefully we've learned that, right? It's a large group, right? So it's not going to if it's an electrophile or an electrophile is adding to the ring it's on, it's probably going to want to go not ortho. It's probably going to go para. So I would say, right? I would highlight para in this case because that's so big. I would be like, you know what? Ortho's probably not going to happen. Okay, but it's an activator nonetheless. The other group that's on here, what else do we have? We have this SO3H, and that's a deactivator. Which way does that direct? This deactivator directs meta. So now we have an issue. Here's the issue. Would you rather go through, right, if you're doing a reaction, a synthetic route, if you're proposing something, would you rather go through where you rely on a deactivator to make your molecules? No, you'd rather rely on an activator. So if you look at this, you should say, well, the only way I can get these two things meta is to rely on this deactivator to get that on there first. No, that doesn't make sense, right? So maybe there was an activator that has since disappeared. Dun, da, da. An activator that was there that is no more, right? So where should we put the activator that was there that is no more? Para to the T-butyl, right? Because we don't want the T-butyl to be near the activator, right? Because the T-butyl is too dang big. So let's propose, if I redraw this. So where would we want to put the activator? If I number the carbons, 1, 2, 3, 4, 5, and 6. Which carbon should I put the activator? 2. I think 2. And what's the one activator we know how to put in place but then take out? NH2, right? So originally, it's not going to be an activator at this point, but it's that diazonium. Right? Which we know one step back is what? The aniline, right? So there's a one step intermediate here, right?
So we should never, rely on, regardless of how things are set.
You don't. Sometimes things are set up that you have to rely on deactivators, but if you don't have to, you'd rather not, right? So like the problem I gave you in the last quiz, the extra credit, that relied on a deactivator to set it up. Yep. So now in this case, now we have our activator on there. Now the question is, generally speaking, what do you think you should put on last? What should be the last kind of thing you put on, an activator or deactivators? You put the deactivators on last. So if I'm working backwards, which group should I take off then? Yeah, so 3, good. And then the next group we're taking off is the T-butyl. And then the NH2 came from what? Nitrobenzene. And then this came from this. Retrosynthesis. Good. All right, so let's do the forward way, right? Because now we actually have to add in the reagents to make this thing work. Don't forget, we still need to do that kind of stuff. HNO3, H2SO4. All right. How do we reduce NO2 to NH2? That of course was H2 palladium on carbon. Actually, zinc HCl also works, but you can stick with H2 palladium on carbon. That's fine. If I want to add the T-butyl group, you could use reagents we did in lab. terbutyl chloride and iron chloride. Yeah. If we want to put the SO3H on, we need 2 H2SO4s. All right. Somebody's got to be the base. If we want to turn into the diazonium salt, remember that's NaNO2, 2 HCl. I didn't ask you to know the mechanism for that. You don't need to know that. But you could. And then the final step, if I want to turn the N2, the diazonium salt, just to an H, that's at H3PO4, right? Which is like an H minus, right? That's why I put the quotes. It's like an H minus. One of those 6 ways to add, to substitute out diazonium salt. It's not really an H minus, but it's kind of like it.
So when it says, do you know the 6 different ways to substitute on a diazonium?
Yep, so this is one of the 6 ways.
This is one of the 6
Yep.
ways.
Other ways are chlorine, bromine, fluorine, and iodine. And then OH minus, and essentially the H minus. So those are the 3 ways, the 6 ways you can change the N2 plus N2 to something else. Right, because this is a nice way to use an activator, right, but then to get rid of it if we want to. Or replace it with a deactivator, right? Bromine and chlorine are deactivators. So you could have an activator there and then put in a bromine.
Why is there 2 H2SO4?
Because you need 2 to make the super electrophile of that one. So go back and look at the mechanism for how that's formed. Right, you need 2 H2SO4s to make that super electrophile. All right, let's look at something. Let's talk about some chemo selectivity. All right, so we'll take the same starting material. Same starting material, but we'll use different reagents, and we'll see what happens. Right, same starting material. And in this case, I'm going to use H2 palladium on carbon. In this case, I'm going to use H2. Actually, you know what? Take that back. I'll use the zinc HCl. So let me see if you can tell me what the 2 products will be. All right, I will draw the products now, and we'll see if you can tell me what happened. So this one, H2 palladium on carbon, of course, is going to reduce benzylic carbonyls. It'll reduce alkenes. Right? Didn't add carbons, didn't lose carbons, right? Down here, zinc HCl is also going to reduce benzylic carbonyls. That's that Clemmensen reduction. It's going to add chlorine. Where, though? There. Chlorine is going to end up on the benzylic carbon.
Why are the chlorines added at some places?
Different reagents. Don't forget, when an alkene is in the presence of HCl, that's the first reaction you guys learned. It didn't, because zinc HCl is, so zinc and the HCl are doing something else, but then HCl by itself, right? Don't forget, so H2 palladium on carbon, zinc HCl, and H2NN, H2OH minus, the Wolff-Kishner, reduce benzylic carbonyls. But that's not to say that those reagents also don't react in other places, right? You guys learned today about OH minus. OH minus could do substitutions and eliminations, but it also helps reduce this.
Tricky.
Zinc and HCl reduce benzylic carbonyls, but you guys should also remember that HCl also reacts with alkenes and alkynes. Yeah.
Remembering back to the alkene reaction, wouldn't it add the chlorine trans to the hydrogen? So wouldn't it be on the...
Well, let's number our. Let's investigate this one a little further. What happened here? There's a hydride shift. But the question should be, why would there be a hydride shift? Isn't that another secondary carbocation? Or is it? Where is this? What position does that chlorine end up on? Are benzoic carbocations, you think, pretty stable?
I think that's.
Right? The whole ring can stabilize it. So let's look at it. So what's going to happen? Pi bond attacks. I'll even number the carbons. 1, 2, 3. Where should we put the plus charge? Hopefully on 2. The less substituted one. So this is already gone, let's say. So we gotta move it up a little bit more. So the chlorine is gonna be, or the plus charge would be on carbon 2, right? Plus charge. 1, 2, 3. Now why would the plus charge, why would there be a hydride shift? Because putting the plus charge on carbon 1 makes a benzylic carbocation, which is next to the pi system, which can then be stabilized by resonance. So this will shift. So even though it's a secondary to secondary, it's not really. It's secondary to secondary benzylic, which is different, right? So it's more stable. So that puts the plus charge in the benzylic position. And of course, Cl- has been floating around the whole time. 1, 2, 3. Chlorine goes there. Get our product. Right? So don't forget your basic, right, chapter 6 stuff, carbocation rearrangements. Right? They'll rearrange if they can have resonance stabilization, right? What's the best way to stabilize a carbocation? Lone pair is the best, pi bond resonance is the next best, and then hyperconjugation is the worst. So, right, if I can, right, normally we say, what do we normally say? You can't go from secondary to secondary, right? There's no even moves, but going from secondary to secondary benzylic, that's downhill. Yep.